Okay, we are going to get started, and I'm going to start the recording as usual. First quick remark. You guys came up with a lot of questions, both during last lecture and since last lecture. That's very good, okay? So keep at it, keep asking anything that comes to mind. That's how you're going to get ready for the IEs every time and do well, okay? So we have our IE1 at the end of the week, this Friday. But we are done with module 1. So now what I'm going to do is I'm going to start module 2. We are going to start it gently, okay? So don't worry too much. Try to stick with me on what we cover today so that you don't have to relearn it on your own, you know, when you do the reading assignment or stuff like that. But no stress, this is not going to be at the exam this Friday, okay? I generally avoid as much as possible to do last minute stuff like that and then immediately the exam. So you will have time to digest it. What's more, this module is actually very nice. This module is very nice because we are going to add to what we've done with the to-do list, for example. We are going to add to what we've done with invoice item and stuff like that. And it's going to be an incremental improvement. It's going to be adding a few features like how do we maintain a list of to-do items? How do we maintain a list of, invoice item? So this is going to be the pragmatic application of this module is really straightforward. But this is going to be also an excuse for us to introduce a little bit of terminology again. Yes, I know there's a lot of jargon, vocabulary, terminology. A lot of you are mentioning that this can be a little overwhelming. That's okay. The good news about terminology is that you can sit down, memorize it probably in 10 minutes just by writing it down and going over it like a few times. The bad news is that the less you are familiar with it, the less useful is any sort of help, like lecture, reading, or somebody telling you, well, you should do this and this and that. Well, if this and that doesn't mean anything to you, of course, it's lost, right? It's not helping you. So watch out with the terminology. It's easy, but don't fall too far behind. So for this module number 2, the reading assignment will be chapter 10, Object-Oriented Thinking. That's the name of the module. It's actually a module that's, like I said, it's really incremental compared to the previous one. And it's also a hodgepodge of different things together. Practical tools that are being thrown into a chapter, probably because they didn't fit anywhere else or they needed to be introduced ASAP. So, as usual, we are going to have a PQ, which is already released. We are going to have a GQ, which is going to be due at the end of the module. I put up a tentative date in Canvas. So again, if you go to the syllabus section of our Canvas site, you're going to see the deadline for GQ2 should be showing already. We have a few practice exercises. So there are going to be 2 types of practice exercise because of the nature of the module. Okay, some of the module is about like managing list of things, you know, and introducing a few concepts alongside. The rest of the module is about, here are a few classes and tools that are very useful, kind of like put them in a pile, you know, and we are going to sort it out together. So because of this structure of the module, there's going to be 2 kinds of practice exercise. The first kind here is the BMI class, the MyInteger class, an ATM machine and a calculator. These exercises are on the most important part of the module, I would say. Okay, they're not the detail-oriented one. We are going to have, with those 4 examples of exercise, good illustration of what you should expect at the next IE. IE2 would be covering module 2, and module 1, of course, it's always incremental, you know, comprehensive. But you are going to see that those exercises are the closest to that. So start them as soon as possible. You are going to see we're going to introduce very progressively the stuff. The first 2 are very, very, very aligned with what we are going to cover on the lecture. The third one, the ATM machine, a little bit more challenging. Okay, not terrible, but a little bit more challenging. So if you get bored with the BMI class, you know, skip immediately the MyInteger class and go to the challenging one to see if you're okay with it or not. Okay. The deal is for you to find your zone of comfort and to find the edge of your zone of comfort. This is where you are going to learn the most, by pushing a little bit on that. And then the last one, the calculator. That one is a good workout on strings. So we already covered strings in COP2513. We covered them a little bit during our review, as much as time permitted, okay? We are going to iterate a little bit more over them. So from the object-oriented programming perspective, I'm going to use string to illustrate something that is a source of bug in Java. Okay, but from your perspective, if you still have problem with strings because you didn't transition well from Python to Java, for example, or anything like that, whatever, that's your opportunity to catch up again on string. And I'm going to try to help you do just that. Okay, so to help you do just that, we have Coding Bat. I just listed a few of them here, but Coding Bat has actually 2 sections on strings. So if really you want to catch up on string, you can pick up any of these exercises, work on them, and come to office hours for help. We'll be happy to help you with anything that you bring to us during office hours. And then there are some exercises in the chapter that is assigned as reading assignment that are also very good exercise about string. These ones are a little bit higher level than the Coding Bat stuff, okay? Think about Coding Bat stuff. I need to, for example, review a little my COP2513, or I need to, again, work on my transition between Python or C# and Java. Then Coding Bat exercise are exactly what you need first, okay? The textbook exercise, they go a little bit deeper in string, a little bit more on the object-oriented programming aspect. They're a little bit more challenging, so make sure that you're comfortable with the basics of strings before to jump into them. And by the way, the chapter on string, that is, I don't remember the exact number, but it's one of those chapters between chapter 1 and chapter 8. The chapter on string is really good for a quick review or for a quick reference, okay? You can Google up references of methods on string if you want, but the textbook has everything you need and neatly arranged in a table. And most importantly, it doesn't have what you don't need. Okay, it sounds stupid, but if you Google at large, sometimes you get a lot of responses. You have to sort through it to figure out which one are relevant, etc. The textbook should be actually your first go-to, when you are looking up a reference on, I don't remember, for example, what kind of methods are available for strings in Java. All right. And then we're going to have 2 more practice exercises. I'm going to put them out here at the beginning so that you can start working on them as soon as you're comfortable. Depending on how we do with the schedule, I might even do one or both in live coding session as a review session. If I have time, I will definitely try to do another review session like we did last time. Okay. The 2 exercises are going to be based on the to-do item class that we did already as a review this time, and the invoice item class that I gave you as being the IE1 from 2020, okay? We're going to take those classes and we're going to extend them. As I mentioned already at the beginning of the lecture, our goal will be to add 1 more class to each of those projects, and that class is going to manage, they are going to manage respectively a list of to-do items, or a to-do list, and a list of invoice items, that is an invoice, okay? And we're going to do some processing on all the elements of the list. So we are going to also review a little bit with that arrays, stuff like that, okay? So if you have still problem with strings and arrays, this is the last module where we are going to have an opportunity to have a little bit of time so that you can review, we can help you, etc., get you to catch up, okay? All right, so pretty much what you have on this slide is the exercise. But every semester when I show it like that to students, a lot of them look at me and say, I don't have any clue what you want us to do. So let me clarify a little bit verbally, okay? What we have here is we have 3 classes, to-do, or to-do item, like we called it actually, to-do list, and test to-do list. The test to-do list, you only need the main. There's nothing else on the slide. Why? Because I expect that you know by now that the main is going to be there to test actually to-do and to-do list, okay? So there's a lot of assumed stuff on this slide. That's why it's not clear, right? So I'm going to clarify it for you, but I want you to also get used to the kind of stuff that I'm going to expect you to assume, right? So, for example, here to-do class, what's all this? Well, these guys here, definitely you might remember them. They are attributes, right? So these are all the attributes that we need in the class. Where are my data types? Well, let's see. Can I infer the data type by myself? A title, yeah, that should be a string. A description, a string. Date created, well, that one is easy. That's a date. Date completed, a date. Is done, well, is done is true or false, so that's a Boolean. Okay? So I am not saying that I'm going to do this kind of stuff during intermediary exam and finals. But at the same time, while I'm trying to kind of shelter you from ambiguity during the exams that we have together, at the same time, I want you to be exposed to those kind of quick notation and kind of tacit assumption between colleagues. Because when you talk to colleagues, they are not going to spell it out all for you. They are going to tell you, I want 1, 2, 3, 4, 5 attribute. And if you tell them, well, hold on, what is the data type of the attribute is done? Then they start looking at you like that, they tilt their head and they're like, okay, are you kidding, or are you joking with me, or stuff like that. So we are trying to get pretty much closer to the real way to communicate about those things. What about those? To do, that's a constructor. That's a constructor with no arg. I don't need to know anymore. Okay? To do string title, string description, that's a 2-arg constructor. I know exactly, because of the name of the parameter, which attribute is going to take care of initializing. The one thing that's really missing here, and that is there's no way to assume it correctly, okay? The one thing that's missing here is, do you want the date created to be set, when you create the object, or do you want it to be set later? So I keep looking and I see there is a toString method, a isDone method, a setDone method. So it's going to allow me to set the isDone, attribute, and that's it. So there's no way to set the date at which the task was created. So I'm going to assume that, it's going to be done in the constructor. But I'll give you that, yes, that's what I'm stretching a little bit the limits here, okay? I'm making a lot of assumption. To-do list class. So that one is going to have an attribute named task. I don't give you the data type of task, but I tell you it's going to be an array of to-do objects. So for us, it's not going to be called to-do, it's going to be called to-do item. I'll fix the slide, sorry about that. But bottom line is that we want an array of to-do item inside of our class, and we're going to use that as our list of to-do items. We need a capacity, a size, so capacity of the list, how many to-do items we can store in it. This is a term that's commonly used, so you'll get used to it. Size of the list, that's how many items are actually in it. Easy to remember. What's the capacity of this room? I have no clue. Let's say 90 students, right? What's the size of the population of students in this room? Well, if we count, we are going to get like maybe, 30, 40, 50. I am really bad at estimating stuff, okay? So bottom line is that this is the same terminology that we use for any container in programming as well. So any list, any array, anything of that nature is going to be having a capacity and a size. So once you're familiar with that, somebody tells you just capacity and size, bingo, you know what they are talking about. To-do list in capacity, a no-arg constructor, one-arg constructor where you set the capacity of the list, and then add one element at a time to the list, and toString, so that we can get a string that represents all the contents. And once we are done with that, this is going to be all news, because I guarantee you that once you do the to-do list, exercise, and even if you need a lot of help, once we get you through that one, then you look at, okay, now we want a list of invoice items. That's going to be so analog, okay, so similar, that you're going to apply everything that you just learned, get some good practice, and then you'll be ready for IE2, okay? So that's the plan. The content of this module, it's a little vague, okay? Like I said, I'm guessing the author needed a chapter, the author of the textbook needed a chapter where a bunch of little tools were going to be introduced, and then you needed something to wrap it up with a nice bow. So the concept here is, while in the previous chapter we looked at the syntax, the basic syntax of object-oriented programming, constructors, methods, attributes, visibility modifiers, all that good jazz. Here we are going to try to take a little higher level perspective and talk about how to structure the code. The interesting thing is that from the syntactical perspective, you guys are getting a break, which means that I'm not going to introduce that much syntax during this module. I'm going to use things that actually we know already how to write, but I'm going to kind of drive down the idea of what are the implications of using those things, and what are the concepts in object-oriented programming that are actually made possible, realized by those syntactical constructs. So the details are here. As with every module, I try to give you the roadmap of the module that is from the textbook. So these are all the learning outcomes from the textbook. The first one's very conceptual. After a while, we get into things such as, for example, how do we do conversion between wrapper classes and primitive data types. So it's a little bit more technical, and it's a little bit more like, detailed tool. Here's a feature of Java. So clearly two separation. We start very conceptual, very high level, very easy, and then we move progressively into a few like kind of isolated details that have not necessarily much to do with one another, but that we need to cover at this point in the lecture. Okay? As usual, what is in red is what's generally the most difficult. So this is what we focus on during the lecture. The rest is in the reading assignment. All right. So there are two core object-oriented concepts that I've tried to carefully avoid defining until now. But you've heard me use the term abstraction and encapsulation, mostly because once you've learned those terms, it's very difficult to carry on a conversation about programming without ever mentioning abstraction and encapsulation. But I never formally defined them. So you might have actually a very good idea already in your mind of what I was referring to. That's good. That's perfect. But let me make sure, and let's go over a definition here. So abstraction means that we separate the implementation of something, a class for us, because we do object-oriented programming. We separate the implementation of a class from its usage. So what does that mean? That means that in Java, technically, I could write a class, like the class invoice item. I could compile it. Here's my .class file. So I keep the source to myself. I keep the .java file, but I give you the .class file. And I give you a documentation that say, hey, these are the methods that are public in my class. These are the attributes, if any, that are public. And this is pretty much how you use a class. You construct it, the constructor expects this, and then you can call this method, it does that, this method, it does that. So all I give to you is a list of methods, pretty much, with a phrase or a sentence of two to explain, what they do. And with a list of methods, you have for each method the value that it returns, if any, and the list of parameter, if any. Okay? So now you're ready to do what? You're ready to take that .class file, put it in your current folder where you have your other files for your current project. And then, in your other files, you're going to reference my class. You're going to create objects. You're going to call my method on those objects. And then you're going to compile the whole thing. You don't need the .java file. Even a non-professional IDE like JGraph, and by non-professional, I'm not trying to diss on JGraph. It's a good tool, but it's more of an educational IDE. That's what I mean. Even in an educational simplified IDE like JGraph, it's going to be able to take the .class file and pretty much merge it with all the other .class files resulting from compilation of your source files. Okay? Put all of that together and run it. So what does that mean? That means that there is really a way for you to not have to worry about how I implemented, for example, the invoice item class. I can deliver to you some code that's usable, and you don't care about the source. Have we done that before? System.out.print. I never looked at the code for system.out.println. Not curious about that. Scanner. We have been using the scanner. We never actually even worried about where the Java file for the scanner class is located. Okay, as far as we are concerned, the JDK distribution could have just a .class file for that class, and I'm perfectly fine with it. Okay, as long as I can compile and use it, I'm okay. So that's the idea of abstraction. The idea of abstraction is, I would call it controlled ignorance. Okay, meaning that it's morning, you are late for your commute, you jump into your car, you turn the key, you press the button. You might not know exactly what's going on in the car. You might have a more or less vague idea of what's going on, okay? Something about explosions happening under the hood. But the bottom line is that you can operate the car without that knowledge, okay? Of course, if you are starting to think that there's a herd of gremlins, pulling your car under the hood, maybe one day you're going to get into trouble, okay? Because you are like way too far from reality. But there is a zone, a comfort zone here, where we can safely ignore some of the details and still be able to operate a machinery, use a class, reason about, a certain field or something like that. So this is really what abstraction is about. Abstracting away the details so we can focus on just a few things that allow us to use that class, for example, in our code. And what about encapsulation? Encapsulation is the idea that you can put things together in packages. And when I say package, I don't mean package in the technical sense of Java package. I just mean as a box, right? I want to box things together. What do we have that allows us to do that? Classes. Classes are awesome. They allow us to put variables, and methods together in a very nice little package with a bow on top of it, okay? And what's more, they allow us to hide away details. Some of the methods that are really just for me to implement my own class, I don't want anybody to call them on my object. I hide them. Visibility modifiers. My attributes, oh hell no. Nobody is going to set to -1 an attribute that is meant to be always positive. I make it private. Okay, so we have already the tool, the syntactical tools to control actually encapsulation. So we have abstraction on one hand, we have encapsulation on the other hand, and if you are like me when I was a student back when, then the two terms are kind of like overlapping. So I want to make sure that nobody leaves this lecture, with a confusion about, well, abstraction is kind of like encapsulation, or maybe one of them is necessary, one of them is not, one is a subcase of the other. I don't know. Let's figure it out, okay? So let's consider 4 possibilities. 1, abstraction and encapsulation are equivalent actually to one another. It's maybe not a situation like we have had already many times in this course where it's a complete synonym, but conceptually they are equivalent. Second possibility, B, they have nothing to do with one another. Doesn't mean that one is useless or anything like that. That just means that there are two, we would call them almost like orthogonal concepts, okay? They cover completely different things. C, abstraction is necessary for encapsulation. And D, encapsulation is necessary for abstraction. So take like 20 seconds or whatever, 30 seconds. Think about it, pick one. And try to come up in your head with a justification. Like if you had to not only pick one, but defend your decision. When you have set your mind, give me like a little thumbs up or something, so that I know that you guys are like, cool. So let's talk about that a little bit. How many people are in the A group? Nobody? Okay. Interesting. How many people in the B group? How many people in the C group, maybe? Okay. About like what? A third, half? How many people in the D group? Okay. So you guys have good instinct. You avoided A and B. All right. So that's cool. So it's about dependency. There's a dependency built in between abstraction and encapsulation. Now the question is, it's easy to get it wrong, because again, the two concepts overlap. So we need to clarify that. We need to delineate exactly, which one is dependent on the other. So A and B, no. They are not equivalent to one another, and they do overlap with one another. What about abstraction is necessary for encapsulation? That was a trap one. No, abstraction is not necessary for encapsulation, okay? But encapsulation is necessary for abstraction. That means that you can look at abstraction and encapsulation as two complementary facets of the same idea. It's the same idea, right? The same idea is to put stuff together, make it a blob that we call a class, and then hide stuff away so that people can use the class without knowing all the detail. So that's the definition of abstraction, and that's exactly what encapsulation does. Well, that's it. Abstraction is a concept. Encapsulation is a tool, is a mechanic. Okay? So when I talk about encapsulation, I talk about writing classes. Classes is a tool that allows encapsulation in object-oriented programming language. Function in Python, they serve the same purpose. Okay? So you don't have to only go with class to do encapsulation, but anything that's meant to put things together, cut together like that, is going to provide you a tool to achieve encapsulation. And visibility modifiers, the ability to hide like data or methods, that's also part of encapsulation, but all of those are tools. What do we use those tools for? Well, we put things in classes, and we use visibility modifier to restrict access so that we may have abstraction. So one serves the other. That's it. Okay? Once you have that picture clear in mind, then you should be okay for the rest of the semester when we start talking about encapsulation abstraction more and more often. This is the only possible way that I've ever seen a student misunderstand those two concepts. Okay? Now we're going to introduce another idea, another concept. And again, we have been writing classes, we have been using visibility modifiers, so we know already how to do encapsulation. And because we know how to do encapsulation, we already did abstraction, just we didn't call it that way. Same thing here with associations. Association, what does it mean? That means that one or several classes can have relation between one another. And the jargon that I'm using right now should start like jolting your memories a little bit from the intro to database that you either have taken already, are taking currently, concurrently with this course, or you're going to take it very soon because it's one of the 4 prerequisites, right? So in databases, you talk about tables. In SQL databases, you talk about table, and you implement with tables relations sometimes, right? So you have those diagrams, those entity relationship diagrams sometimes. I don't know if this is how you have been taught, but you can have a diagram that represents all the entities of your application and their relation with one another, and you implement those diagrams using table and relational algebra. Okay. We have the same kind of stuff going on with classes, okay? We can say that one class is in an association with another class. So it's a form of binary relation. For example, here, on the small diagram that we have at the bottom, we have 3 classes: student, course, and faculty. And that would be the UML diagram, the very simplified UML diagram, where we not only list all the classes that we have, but we list also the relation between those classes. So we use arrows to connect the class, to show what direction the relation is going. And we use numbers to represent how many objects of each class are involved in each of the relation. So for example, if I look at the relation on the right, so the arrow tells me it's read from right to left. So that means each faculty teaches between 0 to 3 courses. Okay? That's how we read the numbers on the arrow. We read right to left because of the arrow. The name of the association is teach. So each faculty teaches 0 to 3 courses. And then we could have the inverse relation. Okay, we're not going to go in detail and you know, consider case here where it matters if we have only the relation in one direction or the other. But just to let you know, yes, I could read that relation in the opposite direction and say, for example, each course is taught by exactly 1 faculty. We cannot have a course taught by 0 faculty. I mean, that would be probably a dream for some administrators in universities, I guess, save some money. You cannot have a course taught by 50 different faculty. That would be a little messy. All right, so we set the rule with those numbers that we call the arity of the relation, okay? And then we have another relation here where we say pretty much each student, so the arrow tells me it's read left to right, each student takes star, meaning any number of course, okay? That's really optimistic, okay? That's if you go over 4 per semester, you're going to probably have some problem, but anyway. And then we can read it the other way, saying that each course is taken by between 5 to 60 students. We have less than 5 students. The course is not offered, it's cancelled. We have 60 students, that's it, the cap for the course is filled. So I don't know what university has a 60 student as a cap, but it's not the case here, definitely, you know that. So that's it. We can write relations like that, and we can even have relation from one class to itself. It's a kind of an odd case, but it's not that weird. It's not that weird. It's not that difficult to comprehend. For example, I can have a class person that's going to represent, you know, somebody in my company that works for me, an employee. Okay, should have called that employee actually. And that person can have a relation, can be in a relation called supervisor or supervise somebody else. Okay, so in this case we have each person has 1 supervisor, and each person who is a supervisor has 1 supervisee, I guess that's a word. Okay, maybe I'm making up words. So we can define relations like that are just self-referencing, okay? And we still use arrows, we still use RET and stuff like that. It's not really conceptually different. How do we implement relations in general, and that relation in particular? Well, I could have a class person, and inside that class person, I would say I have a private attribute named supervisor, and that supervisor is, what is the data type of supervisor? Person. So supervisor is an attribute that is a reference, that is meant to hold a reference to an object of class person. Can it be a different person? Can it be the same person? Can I be my own self-supervisor? Yes. According to this implementation, yes. All I have to do is put a reference to an object of class person. Maybe myself, maybe another person, doesn't matter for Java. Okay? So this is how you implement associations. You simply have inside a class an attribute, which is a reference attribute, that's going to refer to an object, maybe of the same class, maybe of another class, and pretty much build that association between this object and that other object. This is an employee, this is an employer. Okay, this is a manager, this is a team worker, etc. All right. What do you do when you have RETs that are not just one? Like as long as you say, for example, a course is taught by one faculty, well, inside the course class, you can define an attribute faculty or teacher or instructor, and that's going to be of type faculty, and it's going to refer to an object of class faculty. Okay, it's going to tell you who is teaching that class. Perfect. So we can accommodate 1 and 0 like that, as far as RETs go. But what about when you have like, up to n? Like 5 to 60 students can enroll in a course, for example. Well, this is where you are going to start using arrays. So for example, here in the second example, in the class person, we have an attribute named supervisors. So now we allow everybody to have multiple supervisors, lucky person. How do we store the reference to all those supervisors? There are many different ways. We can use array list, things that we haven't covered yet, or we can use what we've covered so far, which is an array. A good old-fashioned array of references to person object is going to do the trick and allow us to keep track of exactly all the supervisor that this particular person object is having. Okay? Last concept. So we talked about association in general. Now we're going to try to distinguish different types of associations. We're going to talk about aggregation, and we're going to talk about compositions. And the main reason for which I introduced this, I'm not going to try to trick you on the difference or stuff like that, but it's important that you are exposed to this vocabulary again for every time you are going to look up information either in documentation or on the web regarding object-oriented programming. Okay, there is a distinction. You might as well learn it while you are here. So associations, we know what they are. What's the difference between an aggregation association and a composition association? So there are subtypes, okay? Well, let's start by the things that are common. Both of them are obviously association. There are subtypes of association. And both of them are implemented the same way. So if they are the same conceptually, and they are the same in terms of implementation, meaning that when I have an aggregation, I'm going to find an attribute that is a reference to another object inside an object. And when I have a composition, guess what? I'm going to find an attribute that is a reference to another object, or maybe an array of attributes in both cases. So it's the same implementation, it's the same concept. So for that reason, a lot of people don't even bother differentiating them, and honestly, I don't blame them. Every semester I question whether we should or not, spend the time to go over this. And so far my answer has been yes, let's do it, because otherwise there's confusion that creeps in explanations. And that's the second thing, that some people just ignore the terminology completely, and those people generally end up talking about composition and aggregation interchangeably, like if they are synonyms, but they are not synonyms. And they have some implication on how your code is going to behave. So we need to clarify that right now. We will try our best, and the textbook does the same, to use the proper term, in the proper context in this class. So let's start with aggregation. So an aggregation represents a special types of relation between two classes. It's called a has-a relationship. Okay, like for example, a student has an address. Okay, so this is a very generic type of relationship. It implies some form of ownership. Okay, so we talk about, in that relationship, we talk about the aggregating object. And when we draw the arrow between the two classes, there's going to be an empty diamond, on the side of the aggregating object. This is the object that contains something else. This is a container, okay? And then it's going to be associated to an aggregated object, which is what is contained in the first object. So a student object, you can say, contains an address. Contains an address object. Again, that doesn't mean that the address object is inside in memory, right? You know how this works. The two objects are separate. There's just a reference going from an attribute to the student object to actually the address object. Okay? That's how it works. All right, so we can define our relation, for example, lives at. So each student lives at one address. So I can implement this by having an attribute address, inside the class student. And that attribute will be a reference to an object of type, address, of class address as well. And an address is assigned to between 1 to 3 students. So we're talking about dorm rooms, we're talking about roommates here. So you can have up to 3 students at the same address. So we define our association. We are going to call this an aggregation because there is a sense of ownership. The student owns an address. The address is owned by each of the students. Okay? And as I mentioned, we're going to implement them very easily, just using the same trick that we covered when we were talking about association. So we just use attributes, and those attributes are reference attributes, and they allow us to connect one object to the other. Okay. So for example, here, the address of the student appears as an attribute inside the class student. Okay. What about compositions? So we know it's going to be very close because they would be implemented the same way, and they are also a form of aggregation. So the concept is very, very similar. So what is the difference? The difference is captured in this definition right there. An aggregation is a form of composition. Sorry, an aggregation is a composition. So composition is not only a subtype of association, but it's even more specifically a subtype of aggregation. Okay, so you have association, the general term, then you have aggregation, and then you have composition that are a subtype of aggregation. So an aggregation is a subtype of composition. An aggregation is a composition. I keep making the same mistake. If and only if the aggregated object existence depends on the existence of its aggregating object. So aggregating object, like student address, right? Example. The student is an aggregating object. The student has an address. The address is an aggregated object. It's actually owned by a student. So think about container and item inside the container. Okay, the aggregating is the container. The aggregated is the item that we're going to put in a container. Okay? All right. So what does that mean that the aggregated object existence depends on the existence of its aggregating? That means that the item cannot survive its container. Let's take an example. Let's say that we are trying to model a simulation of the campus. Okay, we are writing university sims or something like that. We have a class that represents a building, all the properties of the building that are relevant to our little game. And then we have a class that represents a room, a classroom inside the building. And then we have class that represent chairs, whatever, any objects that we want to model in our simulation. Okay? When I construct my building, I'm going to construct the classrooms, inside, and then I'm going to put them inside the building. So I'm going to have reference from the object that represent a given building to the objects that represent each of the classrooms inside that building. If I destroy the object that represents a building, that means it's no longer in my simulation. Somebody drag and dropped it to the trash, okay? Do I need to keep the objects that represent the classrooms inside? No. That's what they mean by life cycle of an object. That's what they mean by the object existence depends on that of its aggregating object. Okay? If I destroy the building, the classroom gets destroyed physically in the real world. If I destroy the object that models the building in my simulation, the objects that model the classrooms are no longer relevant. They cannot exist on their own. Okay? It's not always the case. All right? For example, you can have an example of a student object and a fraternity object. If you dissolve a fraternity on your campus, okay, you have maybe an application that keeps track of memberships and stuff like that. You are going to destroy an object of class fraternity. That fraternity is gone. And then what? You're not going to take the student and shove them out of the university, right? The students remain in your system. They can still enroll to courses. They can still pay tuition. They can still do all sort of things, right? So there is a subtle difference here. It's not conceptual. It's not at the implementation level. It's at the design level. So as I explained very early in the course, we are not going to do a lot of object-oriented design. It's a field in its own, okay? We are going to put ourselves in the shoes of the programmers that are going to receive, for example, a UML diagram from a team of designers, and we are going to be in charge of implementing, that UML diagram, for example, in Java. So our job is to understand enough about the design decision, the design process, and the design terminology that we can reliably, make those designs come true. So that's what we need to know about aggregation and composition. The problem with this is that it's becoming a little bit of a gray area. And maybe this is not subjective per se, this is not a gray area really, but at the very least, give me that, this is something that is highly contextual. Meaning that if I use examples that are, directly connected to the physical world, like buildings, classrooms, everybody is okay. If I start using more specific example like student records, tuition forms, stuff like that for an application that's used to manage, your university, then it's going to be a little less intuitive. Do I keep a record of all the tuition payment of a student even after that student left the university? As a matter of fact, do I keep their transcript? The answer is definitely yes in that example. So do I keep the whole object that represents the student in my database? You see those kind of questions? So those kind of questions, generally they have an arbitrary answer. Arbitrary means whatever your client is telling you to do. So this is go back to the requirement, and if the requirements are not clear enough, call a meeting with your client and ask them, okay, what do you want to do with those objects once the student, for example, graduate? Do you want to keep them? Do you want to archive them? Do you want to, etc.? And those discussions are what are going to sometime allow you to distinguish between composition and aggregation. Because now you are going to better understand the relation between objects and the dependency in terms of life cycle. So the more realistic the problem, the easier it is to either figure it out or ask the client, call a meeting with the client, and further clarify the initial requirements. The problem in a classroom like this one is, by necessity, we look at small examples, things that are not complicated from the perspective of the domain that we are trying to apply our technique to, but so that the only difficulty you have to deal with is the difficulty of the technique or concept or terminology itself. When you do that, it can get ambiguous. So word of warning, we are still going to try to do it, but I want you to keep that in mind as we go over the following examples. So here's the first example. So I didn't use the notation for aggregation composition. I just put a circle, right, on my arrow. So that's because we don't know yet if it's an aggregation or a composition. So I'm going to say I have a class student. I have a class Greek society, like a fraternity. And I think I already gave that one away, so that's going to be super easy. And we have a relation as members. That's red, right to left. So each Greek society has 1 to n, whatever the value of n is, a maximum number of members. So it's not star, that doesn't mean any value. That means a specific range that we decided. Okay. So is this an aggregation, a composition, or neither? So since I kind of gave it away, just say it out loud. Aggregation? Yeah. Why? Because composition is stronger than aggregation. Composition would imply something about the life cycle, okay? Maybe I want to keep my Greek society even if I have only one student in it, okay? But for sure, if I destroy the Greek society, I don't want to do anything to the students, okay? So, this one is pretty trivial, okay? So A, clearly an aggregation, even without more details about the application that we're trying to write with those class, I can figure it out just by using common sense. What about this one? I have a class student that contains all the information about an undergraduate student, for example. And then I have a class grad student that contains all the information about a graduate student. So there is a relation between the two. That relation is called is a type of. So each graduate student is a type of student, okay? So each graduate student contains all the information that an undergraduate student would have, plus more. For example, who is their thesis advisor, stuff like that, okay? All right, so what about this one? And for this one, we're going to do as soon as you figure it out, we're going to do a quick show of hands. So I'm giving you like a few seconds to think about it. Once you choose one, think about the justification, okay? How would you justify this to me, to a classmate, to yourself, in an exam or whatever? Don't pick randomly. Even for that works sometimes. So, who is for aggregation? Okay? Who is for composition? All right. And who is for the catch-all answer, neither aggregation nor composition? All right, so there is unanimity. Everybody who voted for actual composition, except if I missed somebody, and I apologize if I did. So why do you guys think it's composition? Yeah? Makes sense, right? So all the information about an undergrad is also a part of the information about a graduate student. So things like the U number, etc. Okay, that makes sense. Except that the actual answer is C, and it's a trick question. Okay, I didn't expect anybody to actually select C. Nobody ever selects C. It's always A or B. But I want to use that just to illustrate something to you. Is that the same way aggregation and composition are really similar. Okay, but there is a subtle difference. We are not done with all the association we're going to talk about. There are other type of association, and that one chapter that I told you about at the beginning of the class, the one on inheritance and polymorphism, the one that I told you would be the peak of difficulty for the semester, and then we come down a little bit. That one chapter is going to be entirely about a relation between class. That relation will be called inheritance. We are going to say that one class inherits from another. So it's no wonder that composition is chosen here instead of inheritance, because there is a big, I don't even know how to call this anymore, maybe a big debate or something like that at the design level in object-oriented programming, where people say, for decades we have been using inheritance like crazy, like if it was, the solution to every problem. But now people are discovering that in many problems where we would use inheritance, and this is a problem typically where we would use inheritance, we can also use composition. And there are benefits to both approaches. So when you hear people saying like inheritance, nobody uses inheritance anymore in object-oriented programming. That's not true. Okay, we still use it. It's still being used a lot in every of the framework that you are going to encounter. Inheritance is used. But it's true that since its inception, we have discovered since then that composition and inheritance actually are very, very close types of relationship. And again, like with any situation where it's close, you can spend your life trying to defend one instead of the other, or you can try to figure out which one is applicable to which category of problems. And that's what we're going to try to do in this class. Okay? So yeah, composition would be actually acceptable in the context of everything that we covered. So you guys did well. What about this one? A student is known as a name object. And by the way, name doesn't have to be a complicated class. It could be even a string. The string class. So the class student would have an attribute named name. So full name, let's call it like that. And that would be a reference to a class, an object of class string. Okay. Here I'm saying an object of class name because maybe inside that object I have a first name string and then a last name string and a middle initial and whatever you can imagine there that would constitute a name. Okay. So what do you think? That one should be faster, right? How many for aggregation? Aggregation is not popular. Huh? How many for composition? Composition is popular. How many for it's not aggregation or composition? That guy over there? Oh, thank you. Actually, I thought you were joking, but all right. Thank you. All right, so, okay. Nice. Let's take a look together. So this one, composition, okay? But we've talked about composition and how it's close to inheritance, things that we didn't cover yet, okay? So that means that we could potentially implement this one, with composition. We could go with inheritance, maybe. Is inheritance applicable to this one? No. But it's not fair to trick you on that because we haven't covered yet inheritance, okay? So that one is a good example of composition. But it's still starting to taste a little weird. It gives us a bitter aftertaste because, so I need more information, what's the name of a student? Is it just a string? If it's just a string, John Smith, yeah, I can ditch that object, as soon as I'm done handling the record for that student. But do I want to somehow optimize things? Is the name class actually a big class? It has a lot of stuff related to the name inside of it. And if two students have the same name, exact same name, then I want to have both of those student objects reference to the same name object. Wow, if I start doing that, then there's a problem, okay? If I start doing that, then it's no longer a composition. When a student goes away, I don't necessarily destroy the record of his or her name. You see what I'm saying? So the idea is we are trying to push those examples, and I know it's frustrating. As a student, it would have frustrated the hell out of me. But it's just to make you understand where are the limits, okay, of what you can very easily ascertain, common sense, example, easy peasy, and when as quickly as possible you can get into trouble trying to ascertain whether it's one type of relation or the other type of relation. Last one, student account. We're just going to process that one like that. Student account and a registrar database. That one is the example of, I need more information. I really do. Because I stretched as far as I could my common sense, all right? But this one here, I don't know if you want to keep track of students after they graduate. That's the main question. So there is no solution to that. It's either it's in the requirements, and I've overlooked it, or it's not in the requirements, in which case we need to have a meeting with the clients again, and they need to clarify the requirements. As long as you are in the university, except if you take a software engineering class, your requirements are going to be as unambiguous as we can make them for you. Because we don't want to trick you, we don't want you to misunderstand the requirement, and lose a ton of points. But in the real world, the requirements are always ambiguous. And the requirements are never going to be something that you obtain from your client, and then, at the end of it, you refer to this written document during the development, and it's over. Now, there is a whole analysis process that's going to be about refining progressively the requirement up to the point where the people who do actually design architecture of application are going to be satisfied that they capture unambiguously all the requirement, and they are going to be able to formalize this using different artifacts like UML diagrams and whatnot, and then they pass that to the developers that are going to implement the application. So it's not always very satisfying, and that's why I'm glad to not be teaching an object-oriented design class. I'm really much more comfortable teaching an object-oriented programming class because it's a lot more objective. Okay, there's a lot less room for interpretation. But you need to at least, at the very least, be aware. Be aware of those problems. So some of the practice quiz, some of the graded quiz are going to cover that. I'm working on releasing our first peer learning quiz. I'm sure pretty much like half of you, I would bet, have forgotten about those because we didn't use them yet, right? So it's going to be 10% of your grade, no stress. These are really to help you practice and understand concepts like this one that are a little bit subjective, okay? So you're going to see exactly how that works. I'm going to release it either this week or next week, and we're going to go through it together. For now, let's go back to some code that is not ambiguous, or not ambiguous at all, actually, and that illustrates pretty much everything that we talked about until now. And that code example that I'm going to give you, there's going to be 2 code examples, right? Once we are done covering them, you should be able to start this practice exercise right away, okay? So you should be able to start already the practice exercise on string, okay? Because this is, again, just to help whoever needs a little bit more help with strings, okay? But the practice exercise that represent classes, the to-do list and stuff like that, as soon as we are done with one example, you can start already working on it, okay? All right. So we're going to talk about a stack of integer, a class named stack of integer, and a class named test stack integers. Well, so you guessed already the structure. This is the same structure we have been using. One of the class has a main. The main is used just to create objects of the other class, interact with them, make sure that all the methods are correctly implemented, and so on and so forth. What is a stack? Well, that can be this, which is interesting, or that can be this, which is also interesting, but for different reasons. So this is a data structure. So today we are going to, for some of you, we are going to talk about the very first data structure that you are going to ever encounter. So don't worry, I'm not trying to merge, the data structure class into this one. I just want to give you one example so that you progressively get used to the concept behind data structure. So a data structure is a structure that contains data. I tried to make it sillier, but I could not. That just means like an array, for example. An array is a data structure. An array contains a sequence of items, and these items are kept in an order, and these items are numbered. Okay, that's what the index is. So you guys already encountered actually a data structure. What's the difference between an array and what we call a stack? Well, a stack, and we already encountered that term, right? Remember programs execution stack, that zone of memory where we put an activation record, then we call another method, we put a new activation record, this method call another method, we put a new activation record, and then when this method terminates, this activation record goes away. We go back here. When this one terminates, this one goes away. We are back to our main method. When the main method terminates, its activation record goes away. So what did I do? I stacked activation record, and I unstacked them. The concept of a stack, it's like a stack of pancakes or a stack of dirty dish, is the last element that you put on top of the stack, that last element over here, is the only one that you can remove. So the last element in the stack is the first element coming off the stack. And that's just a restriction. That's a constraint. It sounds silly, right? We could use an array to implement a stack. As a matter of fact, we are going to. We're going to use an array where array has different type of constraints, okay, to implement a stack. And the fact that the stack has those additional constraints makes it very useful, especially in computer science, right? When you are trying to model certain problems, like for example, like say, not cellular automata, finite automata, stuff like that, then those data structure come in very handy. But that's not the only time they come in handy. They come in handy also for more pragmatic, I would say, less theoretical application. So we are going to look at it from the perspective of, I'm trying to solve whatever problem, and I need to maintain a stack of integers. So I put the value 3, 6, 9, and then when I want to take values out of the stack, the 9 is going to come out first, then the 6, then the 3. Okay? And those values could be anything I want. So this is what this diagram is illustrating. All right? You have an empty stack. The two operations that we are going to define on the stack, we're going to define a third one too, but it's not essential. The two essential operations are push, where I'm going to call a method push, and that method is going to actually add some data that is passed as argument to my stack. So every time I push, I add some data on top of the stack. And every time I call the method pop, it's going to look at the top of the stack, take whatever is there, return it to me. So push takes an argument, returns nothing. Pop doesn't take any argument, returns a value that was on the stack and removes it from the stack. So I push data 1, data 2 on top, data 3 on top. Then I pop data 3, pop data 2, pop data 1. And now I have an empty stack again, just like the beginning. And that's it. That's all there is to the concept of stack. It's also referred to as a first in, last out type of data structure for the reason that I already mentioned. So let's take a look at first the UML diagram. So what is going on? What is going to go into this class that's going to represent a stack of integer value? So name of the class, stack of integers. Attributes, element, private attribute, there's a minus here. Element is going to be an array of int values. Okay, it's a stack of integer values, so I'm going to represent it internally as an array of int. But if I just used an array of int, people can do all sorts of things to an array of int. They can sort it, they can shuffle it, they can add at the end of the array, they can add at the beginning of the array, they can resize it maybe, stuff like that, right? So I don't want them to just have an array. I'm going to construct a class around the array. It's going to be composition, by the way. The array is going to be composed into the class stack of integer. And I want to restrict what you can do with that array so that it behaves like a stack. So I'm going to have another attribute called the size, which is going to tell me how many elements are currently in the stack. And then constructor, create a default empty stack with a default capacity of 16. So there is a concept of capacity here. Maybe it should be also an attribute. We are going to see about that in a minute, okay? But I have a constructor with no arg that's going to construct a stack that has a capacity by default of 16. Then I have a constructor that takes an int value. And this int value allows us to specify the capacity. So construct a stack of 100 slots. The stack is still empty. That just means we have room to accommodate up to 100 elements, or in this case, up to 16 elements, okay? We have a method that returns a Boolean value. That method called empty or is empty, we should really have called it to be consistent. That's pretty much what's going to check for us whether we have any element inside the stack currently or not. And it's useful sometimes to check, is my stack empty before you try to pop a value out of it, okay? And then after that we have peek, which is that third method that is not as essential, but I mentioned that we would have maybe an extra method here. So peek allows you to look at the top of the stack, and that method will return the value that it sees at the top of the stack. So it returns an int value, but it doesn't remove it from the stack, which is the difference between peek and pop. Pop looks at the value on top of the stack, returns it to you, but it also removes that value from the stack, okay? So push, peek, pop. Push, I already explained how it works, right? It push a value onto the stack. And then get size to pretty much gives us the number of elements that are stored in the stack. Do we really need, for example, empty if we have get size? No. Because if we do a get size and the size is 0, that means the stack has a capacity of 100 maybe, but it has 0 element in it. So we could figure it out like that. So sometimes you have multiple methods that are given to you in an API, and you could do, without some of them. They're just there for convenience. So that it's very easy to write things like if my stack.empty, if that's true, then, pop, for example, the element of the top of the stack. That's how we are going to conceptually regard the stack of integers class. Okay? Now let's talk about the implementation details. So the implementation details, we have an elements array. It's an array of a fixed number of int. This is where we're going to store all of our data. Okay? So, element index 0, index 1, index 2, index, etc. We are going to assume that element under 0, element index 0 is the bottom of the stack. This is where my stack starts. And then as I increase the index, I go towards the top of the stack. So as I am pushing element on the stack, I want to add them at the first available index. Okay? Like at the beginning, that's going to be 0. Empty stack means we have nothing in it, so 0 is the first available slot. I put my element at index 0, and then I keep track using the size attribute that I have one element currently in my stack. So if I have one element, it's going to be stored at index 0. If I add another element, I'm going to store it at index 1, and that's going to be 2 elements total in the stack. So there is a relation between the number of elements that I have in the stack, size, and the index that is available to store the next element. Okay? Like right now, I can just look at the size, and I say index 2 is where I store my element. So there we go. I add an element. It's now occupying index 2. I have 3 elements total. 3 is also the index of the next available slot. And I'm going to use that, okay, to know pretty much where is my top of the stack. If I want to jump directly to the top of the stack, I can use element index size minus 1. That's going to show me the index of the topmost element of the stack, the last element that I added to my stack. And then what about the capacity? What is the capacity? We already covered that last lecture. The capacity is pretty much the maximum number of elements you can accommodate inside that array. And right now we're working with Java basic arrays, and Java basic arrays can be a pain because they don't easily expand. You know, we cannot do like we do in Python and just add at the end of the array and automatically the array resizes to accommodate more element. Now in Java, once you said I want a new array of int square bracket 5, that's it. You've got 5 elements in that array. You cannot add a 6th element. Okay? Well, technically you can. That's what we are going to look at in the code here, but it takes work. Okay? Things that are done automatically by Python or in Java by a class called ArrayList. The class ArrayList, as soon as we discover it, you're going to see you won't want to use a regular array except if you really have to. Okay? All right. So this is how we're going to implement the core data structure. We're going to use an array to pretty much implement the behavior of a stack of integers. So let's start with the code that's going to test our primary class, the class that we want to deliver, right? That code is going to be in a class named test stack of integers. Makes sense. That class is going to have a main. Okay, so far so good. I'm going to create an object of class stack of integers. So I'm using the noarg constructor. So according to the comment that was on the UML diagram, that means that this noarg constructor is going to create a stack of size 0, no element in it, it's empty, but of capacity 16. Okay, that was the deal based on what we had, the comments that we had. And then what I'm going to do, sorry, I went a little too fast. And then what I'm going to do is I'm going to repeat in a loop. I'm going to iterate 10 times from index I equals 0 to index I equal 9 included. And I'm going to call on my object of class stack, the push method, and tell it to push the value of I. So I have my empty stack. I'm going to push 0. Then I'm going to push a 1. Then I'm going to push a 2. I'm going to push a 3. So this is how I'm going to fill up my stack up to 9. And then, as long as the stack is not empty, so I'm using that method empty that returns true if the stack is empty, false if it has some values in it. Okay. So while not false, pretty much, I'm going to keep popping data out of the stack. So looking at the topmost value, 9, remove it and return it. Return it to do what? To print it on the screen followed by a space. So on the screen, I'm going to see 9, space, 8, space, 7, 6, 5, 4, 3, 2, 1, 0. That's how I'm going to make sure that my stack is working. I load it up with data, and I know it's going to be the digits between 0 and 9. And then I unload it element by element in the reverse order. So I should see a nice countdown from 9 to 0. That's how I'm going to test my class. What about how I'm going to write the class? So stack of integers is going to have, and this is straight from the UML diagram, it's going to have an element array of int as an attribute. So composition, right? Elements is a reference variable meant to hold a reference to an array of int object. I'm going to have size, which is just going to be an int, and default capacity, which is going to be a constant. So how do you make constant in Java? I mentioned it once this semester. It's not really critical, but it's just very simple syntax. You just add the keyword final. So here I have a public static final. Why did I make it static? I don't know, because I want it to be accessible from the class itself. And this is actually my default capacity when you create an empty stack. Yeah? Why do I use private? That's a good question, actually. Let's say that I use public. Okay, so somebody creates an object of class stack of integer, like my main here. I don't want them to be able to mess around with the size, because they could make a loop like that and add 10 elements to my stack, and then just have a line here that says stack.size equals 0. And then that would completely mess. It would make my code inconsistent. You see what I mean? My code is consistent because every time I'm going to add an element, the method that adds an element to the stack is going to increment that counter, the size attribute. And as long as I do this, the size is going to really represent, what's inside my stack. But if I allow somebody to just arbitrarily, set it to 0, decrement it, increment it, etc., I give them too much control on something that is really an internal implementation detail of my class. Okay? So that's a good example of when you want to lock down things for safety's sake. And it's not necessarily that the other programmers are malicious. It's just that it's worse than that. Sometimes they're trying to be helpful. They try to manipulate the size because they think it's going to be useful, it's going to make the code faster, whatever, and they end up, introducing bugs. All right. So very good question. So we have those three attributes. One of them is a static constant. Then we have a constructor. We use constructor chaining. Okay, so keep that in mind for the exam coming up this Friday. We use constructor chaining here so that the no-arg constructor calls the one-arg constructor, the one-argument constructor, and we pass default capacity. What's the point here? Why didn't we just write 16 here? Because we are trying to make our code as readable as possible. So instead of using the number 16, and then if we want to upgrade this, somebody is going to search for all the occurrence of 16 in our code and wonder, is that the size or is that something else? We are going to just give it a name of a constant, so that it's super readable. So if you don't tell me anything about the capacity you want, I use a default capacity that is defined here in the class itself. Okay? And then if you tell me the capacity, then I create a new array of int that has that number of elements, and I put the reference inside elements. So both constructors end up executing the work that is done in this constructor, just like we have done, with the to-do item class. Then there are parts of the code that are not as exciting, assuming the previous part was exciting to some of you. Get size, it's a getter. It just returns the value of size. Okay? So again, why size? Why do we need a getter? Because size is private, and sometimes we want to know the size. But we are not going to give them a setter so that they cannot modify the size. So we control access like that. And then other methods, so these are going to be the fun one. Push. How do we push something on the stack? Well, you give me a value, I'm going to push it on the stack. First thing I do is I check if the size is greater or equal to the number of positions in my array. The size is how many elements I already have added. So am I actually to the point where I filled completely my array? There's no more room. Okay? If that's the case, those 3 lines of code here are there to create a new array, copy all the values of the old array into the new array, and that new array is going to be a little bigger, and then use that new array to add this element. So this is where I manage myself by hand the extensibility of my array. Once I have filled my array of 16 elements, for example, initially, or 100 if I specified 100, I'm not going to break, if somebody tries to add one more element, I'm just going to have to resize my array. Once I'm done resizing the array, if I had to resize the array, okay, if I didn't have to resize the array, I just add to elements, index, size, the value, and then I increment size, okay? And this works because, remember, if you have like 3 elements, the last index is 2. That's why this line of code works. So I can do that straightforward, or I can actually first resize my array and then do that. Yeah?
Does this go in the main or in the other one?
This one goes in the other class, stack of integer. So the push method would be one of the method inside stack of integer. Okay? Yeah?
Would the old elements get deleted?
Yes. You guys remember who takes care of deleting the old element? Garbage collector. Yeah. So it's 45, so we are going to stop here. But I'm going to leave in the PDF of the slide the pop, pick, and empty method because they are really easy. Okay. And next session, if you have any question about the implementation of pop, pick, empty, because we didn't really cover it live, just let me know. We'll take some time at the beginning of the lecture. Okay? Thank you, everyone.